Welcome to today's podcast. Our topic, logistic functions. These functions are the most common Sigmoid curve or S-shaped curve graph, and they're a way to model growth. Pretty similar to exponential growth, especially in the beginning. So as x is negative, it looks real similar to a normal exponential curve, getting bigger. But eventually, it hits a saturation point, and the growth slows down and reaches maturity. At this point, growth stops, so it has a horizontal asymptote towards the top of the graph, or as y gets bigger. With an exponential curve, look really similar, but it continues to increase forever, continually being concave up. With logistic functions, they're concave up for the beginning. When they hit their inflection point, right here in the middle, they turn to concave down. So they're still increasing, but increasing at a slower rate. There are lots of situations that model this. Applications are found in biology, economics, chemistry, probability, sociology, statistics, even political science. You can think about human growth in terms of a logistic function. When we're babies, we grow fairly rapidly. Then our growth slows down until we eventually peak. Diseases are another example. When the disease is first beginning to spread, it doesn't spread too fast, but then it eventually picks up really quickly, and either as the disease is contained or cures are found, that growth of the spread of that disease will slow down. Populations, in the past we've looked at populations just as exponential growth, like the rabbit problems, or even looking at human populations. But really they're more of a logistic situation. And that's due to factors like food and water, predators, space available. Now I'm going to show you a little applet that will give you a visual example for what we're talking about. So we have two fish in the habitat, and the habitat has a carrying capacity of 1,000. You can see that down here. The birth rate between our fish is going to be 1.5 for each generation. At the top, as it runs, you'll see this number change for generation. That will tell you how many times our fish have reproduced. And at the right, it will give us a population total. So I'm going to go ahead and hit run. You see the fish starting to multiply. Continues. Our population is growing very rapidly. Now, as our capacity is getting closer and closer to 1,000, our growth really slowed down. It's getting closer and closer and closer. Now, in real world situations, it would probably actually hit it, but when we use our mathematical model, we're going to use it as an asymptote up there. Okay, so back to our notes. Now we need the equations for logistic functions. So the first one, we're going to have two different ones. The first one is f of x equals c over 1 plus a times b to the negative x power. Now in this case, a, b, and c are all constants. C is our upper bound, or upper limit. A and B are bases to our exponent, they're multipliers. They don't really have a graphical connection. We will be able to solve them with systems of equations, but there's not really anything I can label for you. We're also going to do logistic equations with E being our base. E being Euler's number, that one that occurs often in natural situations. So we'll have c on top again, being our upper bound, and 1 plus, in our denominator, a times e to the negative b times x power. So this time we still have a, b, and c being constants. B cannot be 0, otherwise we would lose that characteristic of x as our exponent in the denominator, and would no longer be logistic. So that's kind of the only other difference. Both of the examples I've shown you so far are growth examples. When b is positive, it will grow just like the graph that I showed you a minute ago. If b is negative, it's still logistic, it's just decay. So similar to what we've seen in the past with growth and decay. So if I had exponential decay, it would look like this. So logistic decay will look like this. So the upper bound is still an asymptote. There's still that inflection point where it switches from being concave down to concave up this time. And that change in concavity is where my rate changes. And in a decay, it's slowly decayed, and then it speeds up its decay right in here and slows down again. Okay, so what are we going to do with this? Well, because it has so many real-world applications, we're often given data, and we need to find a model that fits the data pretty closely that we can then use to either find points within our data called interpolation or projections beyond our data sets called extrapolation. So let's say we have a story problem where we're looking at the population in a new subdivision. So a builder's coming along, it's putting up new houses, people are buying the houses, and this change in population tends to be logistic. There are 1,000 lots to be sold, so it's cut that upper bound, that limit, so we can connect it to the logistic growth. Also, if you think about it, the population is in a subdivision, nobody's bought the house, eventually a few people start buying, they hit that popularity where lots of people are buying the houses, and then as there are fewer and fewer left to buy, that growth rate slows down. So here's our table. X is going to represent months or time. So at 2 months, 103 of the lots have sold. 2 months later, 117. At 6 months, the builders sold 132. At 8 months, 148. 10 months, 167. Now, as I walk through these next few steps, I encourage you to pause the video and give it a try. See if you can guess where I'm headed. It should help the information stick better if you've thought about it on your own a bit. Okay, so using our general equation, f of x equals c over 1 plus ab to the negative x. We don't have anything about natural log. We have no reason to assume it's going to have that in it, so we'll go ahead and use just the regular ab1. Right away, I have one of the values I can plug in. I know that my maximum number of lots is 1,000. So C has to be 1,000. So I can fill that in my equation. Now if you think back to the other equations that we've done, we have two unknowns, A and B, that we need to have to be able to write the equation. So I'm going to need to use 2 points and a system of equations to be able to solve for those two. When we have data sets, it's a pretty good idea to use the first and last point. So I'm going to write a system of 2 equations. So I have 167 equals 1,000 over 1 plus AB to the negative 10th. And we'll have 103 equals 1,000 over 1 plus ab to the negative second. Okay, from here, I want to get rid of these fractions. Okay, so to get rid of the fractions, we're going to multiply both sides by the denominator. So we'll get 167 plus 167 ab to the negative 10 equals 1,000. And for the other one, we'll have 103 plus 103 ab to the negative 2 equals 1,000. All right, next, with our system of equations, we want to eliminate a variable. But because our two variables are multiplied to each other here, we're going to need to divide. So before we divide, let's move the 167 and the 103 over to the other side. Okay, so that will give us 167 ab to the negative 10 equals 833, and 103 ab to the negative 2 equals 897. Now we should be ready to divide. So divide here, and I'm going to try to leave these numbers 167 over 103 as a fraction for a while so that I don't have the decimals and the rounding errors that might occur. So as I divide, my a's are going to reduce down to 1. My b's, because the base is the same, I can go ahead and subtract the exponents. So my next step, I will have 167 over 103 times b to the negative 8 equals 833 over 897. Now to get rid of the fraction 167 over 103, I'm going to multiply by the reciprocal on both sides. Oops. And that should give me my b to the negative 8 all by itself. I'll leave these two fractions multiplied by each other over here and eventually put them in my graphing calculator. Now, to get rid of the b to the negative 8, you could do the negative 8 root. I prefer doing b to the 1/8 power, negative 1/8 power. So if I type all of this in my calculator, 833 over 897 times 103, over 167 fix that for us. And then raise that to the negative 1/8 power, I'll get my b value, which is about 1.0721. We'll include that too. Now try to leave that in your graphing calculator stored there so that we can use it to find a. Okay, so if I go back up to one of my original equations and plug in my newly found b value, doesn't matter which one, I'm going to go over here, give us some more space. So 103a times 1.0721 to the negative second power equals 897. So I still should have that number in my calculator, so I'll raise it to the negative 2 power, multiply it times 103, then whatever I get there, I'm going to do 897 divided by that answer in my calculator, and we should get that a equals about 10.011. Okay, now that I have a and I have b and I already found c a long time ago, I can write our function for this subdivision. F of x equals 1,000 over 1 plus 10.011 times 1.0721 to the negative x power. At this point, I would encourage you to plug it into your graphing calculator. Unfortunately, I don't have one set up to show you on the podcast yet what mine looks like, but type in f of x and see if it has that same curve that we've been looking at. So my logistic curve, as you type it in your graphing calculator, should have that asymptote up at 1,000. Once you have it all typed in and have a nice logistic curve on your screen, take a look at the table. Are the values for f of x similar to the values in our original table? Do we have 2 going with 103? That should be a perfect match because that's what we based our equation on. What about 4 and 117? 6 and 132? 8 and 148? And then again, 10 and 167 should be a perfect match. Okay, now that we have our mathematical model, we can use it to extrapolate. So that's where we want to project in the future what values will be using our equation. You can either trace, or you can use the table, or you can plug in the value for x. But figure out at month 24, or 2 years later, how many houses will be in this subdivision. You should come up with about 347. So pause the video, make sure that you can find that in some process that works for you. Okay, so the last thing I want to talk about with this story problem is the inflection point. So what does that inflection point mean, and where is it? So this place where the concavity switches, or the inflection point, is where the saturation begins to occur. That is always going to be halfway between our asymptote and our other asymptote. We actually have another one. I didn't put it in earlier, assuming you would recognize it, at y equals 0. So halfway between the two of those would occur at y equals 500. So we can ask the question of when. When is that growth rate going to start slowing down? Okay, so that's it for logistic functions. In class next time, we're going to practice together. The main idea being that now we can model situations that grow really quickly, similar to an exponential curve, and then begin to slow down and eventually growth stops. Hope you enjoyed the podcast and you refer back to it often to prepare for your next midterm.